Welcome back. So in chapter 4, and again, kind of doing some wave tops on this. Again, real good conversation with Kuchemann and some of these flows, the effects that we're seeing. A little less on the analytical, a little bit more describing kind of experimental, but important parts. And so this lecture, we're really going to get into transonic, right? And get into some of the features we're seeing at these kind of transonic, so kind of close, including Mach 1 flows. And I'm going to draw a couple of airfoils, right? And so as you're getting faster in airspeed, then for Mach, this is Mach less than 1, you can start getting zones where there's Mach greater than 1. So a little kind of shock bubble will have formed. And then, and next down, you may have that bubble may grow and encompass the entire portion, and also might be starting to get a little portion of the underbelly of the airfoil as well. And then, you start going faster, and then you'll have ultimately, this would be at Mach equals 1. You may start forming then the shock, and you'll start forming sort of the normal shock here. So this would be Mach less than 1, Mach greater than 1. And then kind of just on the other side of supersonic, you'll then have a sort of well-positioned shock with an angle. You'll have a little regime here. This could be Mach greater than 1, and you could have a regime that's actually subsonic, where it's kind of stagnating, it's going below 0, and then you could be getting the kind of shocks off the back. And so, they have sort of qualitatively different phenomena that's going on, but the real interesting thing happens when you take a look at lift coefficient, and I'll just do CL versus angle of attack compared to, say, Mach number with 1.0. A couple really interesting things show up. So we'll kind of draw it first, and then we'll come back and talk about it. And so you have sort of the standard line. This line might represent our, 2 pi square root 1 minus Mach number squared. This would be what we'd expect for lift curves to do. And then once it's on the other side of sonic line, this will kind of snap to 4 over square root of Mach squared minus 1. Right? But you have a couple of really interesting points along the way. And one of them we'll call A, another B, and then C, and D is where you start kind of reapproaching. And then also put in dashed lines kind of what the drag is doing. And so the drag is going to kind of spike up and do its thing. This is Z drag. Okay, so we definitely know, again, we talked about the kind of barrier at Mach 1. But some really smart people, when they kind of took a look at some of these things, they said, boy, wouldn't it be great? This would actually represent this point right here. That would represent one heck of a system to be able to go design. If we could fly there, then we would see a big lift. Right? And so for the drag that has not yet kind of taken off and gone crazy, there's kind of this really interesting position where you might get some extra lift out of the fact that the velocity is starting to go supersonic over portions of the airfoil. And so that's a lot where the supersonic kind of these transcritical airfoils and things like that design kind of goes. And so, as Kuchemann says, there's quite a bit of art into actually shaping these airfoils themselves. And then, just like we talked in the last section, there's all of the physics and boundary layer theory and actual boundary layers and sweep profiles and three-dimensional effects. Like all of that gets buried into into these things, right? In fact, one of the interesting things that can happen with a shock on the boundary layer, and so I'll draw that over here. You know, you might have, this is a wall, then I'll draw sort of, this is the boundary layer, then sonic line can do something like this. And so this is Mach equals 1. And you know, you could have sort of these shock waves kind of inducing on the, look at our boundary layer. And then you can also, we know sort of from experiment that you end up creating so Mach less than 1 back here, and so you end up creating a pressure gradient because you slowed down. And so if you create a pressure gradient, then your boundary layer is could potentially separate on you. And so then that would look like this, sticking to my colors the same way. That would look like this and then grow. Big boundary layer growth because you have created a separation bubble. And then now that shock wave, Mach equals 1, this is Mach equals 1, and you can have some really interesting curves kind of come off of this. And so, again, that shock boundary layer interactions, quite an interesting phenomena, right? And you know, one of the things that happens, I'm going to come back to this diagram over here, is this peak can actually slide around on you, right? And that one actually we call, I know that color didn't come out great, but this is a buffet. Let's buffet. And so you have, buffet is when this pressure is changing back and forth quickly over your wing, and so your wing starts start buzzing. It can start, you know, flopping pretty hard. So this is actually a pretty significant structural loading. In fact, one of the most terrifying graphs you could ever take a look at is, I'll draw it. Let's see. It's called coffin corner. I'll draw it like this. Usually it's drawn the other way, but I'll try to highlight. Let's see how do I do this. And so it is the lift coefficient, and in fact I think this is normally dynamic pressure indicated, but on a U2 spy plane, I'll describe what's happening. So as you're going up in, sorry, this is altitude. So going up in altitude, there is a corner at which if you slow down, you stall, and if you speed up, you buffet. And there's this really weird tight corridor you got to fly in. And I know 747s have the same sort of thing. There are actually videos of people getting a 747 up to 50,000 feet, and it's kind of nerve-wracking. Because if you're flying there and you're okay, again, if you actually descend too quickly, you'll speed up and you'll hit your buffet limit, and you're done. Or if you slow down, or if you pull up more, you slow down, then you're gonna get into stall condition. So it's pretty wild, but you can actually end up having these really weird corners. Okay, so but if you can design around that, and you can get something called a supercritical airfoil. So a couple things. We'll talk airfoil and area rule. So ultimately, think of an airfoil, and it's Mach less than 1 out here. But then there'll be a corner here, and ultimately a portion here where it's Mach greater than 1, and there's a little kink happening in the flow around that line. So Mach, this is again Mach greater than 1, and then it slows down in the back corner, Mach less than 1. So it's kind of what I drew here, that boundary layer of the shock. It's effectively would be this condition right here. for taking a look at with airfoils. But if it allows you to hit this lift condition, then it's pretty slick. Now, the other thing you have to do from a vehicle point of view is it's called the area rule. And so we know that bodies of rotation, we can actually solve for what has the least amount of drag per frontal area, the best performance. This is where the ogive comes from if you're a rocket, or the Sears hack body if it's a pure kind of from zero back to zero type of shape. And from that, we can deduce what's called an area rule. And so what you might want to do, you want the total area of cross-section. If you're looking at a vehicle, you want the area cross-section, basically cross-section versus surface distance to look like that. And so in the end, you may end up drawing a vehicle that is wasted. So it's got sort of, where the wings are around, it's thin. And so that sort of vehicle may end up having the closest towards this kind of smoothly varying area. And there's actually a really famous story, I believe it was with the F-16, but where one design that kind of tweaked some of that, and they really saw a big, massive performance. So it actually, again, what it's doing is the area rule in particular is actually taking care of this drag portion, where maybe it's instead of, it's going to push it just a little bit to the right because you're a little bit cleaner. And because of that, you can then, with your airfoils designed, take advantage of this condition. You get a pretty massive performance gain. But it can be at, a worrisome, terrifying situation where you end up having a dynamic, a coffin corner, right? So this is called coffin corner. Yeah. So, pretty neat stuff. And Kuchemann does this portion of the book is actually pretty heavy on words, as he just kind of tries to walk you through a lot of these concepts and walk you through some of the physics. Again, it's a little lighter on the analysis because so much of this is just, experimental, observed, and then, but has a massive impact, right? So a lot of these vehicles, we can now look forward, right, to 2024. We've actually seen quite a bit of aircraft designed and achieving higher and higher cruise speeds, right? So I think the latest Gulfstream is cruising at Mach 0.93, and it's really because of technologies like this that it's allowing them to take advantage of this kind of bump up and lift and keeping that drag coefficient at bay. So good stuff. We'll see you next time.